Okay, today we're going to be looking at making a MatLab program that calculates Hohmann transfer orbits off a given set of starting constants. This is what the end result will look like. It takes quite a while to calculate because of the way it does it. It calculates positions every second, but we'll get into that in the beginning. This the code is just over 2 pages. But we'll start from the beginning. And so with any MATLAB script, just clear everything to begin with, and then we're going to define the constants that we're going to use. So those are going to be the gravitational constant, the mass of the big body, and the mass of the small body. So the big body is Earth, the small body is a 1,000 kilogram satellite. This is going to require some kind of basic knowledge on orbital mechanics to understand why things are done in a certain way. Scott Manley has a good YouTube series on it, and if you just type in Scott Manley orbital mechanics, it will come up. So the gravitational constant is this. The mass of the Earth is this. Of the satellite is 1,000. To understand why we're using G, uppercase M, lowercase m, you should probably be familiar with the orbital mechanics equations. They're gone through in Scott Manley's tutorial as well. If you don't understand that or have no basic knowledge on like how orbital mechanics works, this will be quite complicated, and you probably won't get why we use certain. So you just won't realise that the acceleration equation and stuff is different. Then we have the variables that we're going to use, which are the radius of the initial orbit, the initial velocity, or the initial velocity vector, which you calculate using the orbital mechanics equations, and then the initial time, and then the change in time, and so forth and so forth. So R. Now, it's important to remember that in space everything is in the 3 dimensions. So whereas before you might only need the radius 1, with everything radius is essentially a position in this equation, or in this algorithm. The radius is basically a position. It's like a coordinate, and so we need 3 dimensions for it. And we'll start off it starts off in the y point, and then the other 2 are 0. Again, because we're in space, the velocity vector is the velocity variable is a vector. Then we're going to use, and its velocity initially is in the x direction. So if you think the radius starts at, if you have a circle, which is going to be the circle of this radius, we're starting at like 6 o'clock right at the bottom. The velocity property is just going to be, because we're at the bottom, the velocity is going perpendicular to the if you draw the radius out from the center of the body that we're orbiting, the velocity is always going to be perpendicular to that because we're orbiting it. And because we're starting at 6 o'clock, the velocity is going to be solely in the x direction. There's going to be no y direction. And because this orbit is flat, it's not at an angle, we don't need to really worry about the z-axis at all. And so from the gravitational equations, or the orbital mechanics equations, we know that the velocity is based off, the orbiting velocity is based off how far away it is from the body, the center of the body, and how the gravitational constant, how big that big body is, the massive body is. Sorry, I'm trying to read my notes here and talk. So this equation here is working out that x velocity, and the norm is, so if this was actually at an angle, if r was at an angle, so if this was smaller and this was bigger, then it would work out essentially this value by using trigonometry, which is what this does. Why am I getting an underlined? Yes, that's fine. T, the start time is 0.0, could be 0. dt, which is the change in time for every calculation, is going to be 1 second. Now delta v is the initial change in velocity at a certain point that is going to result in us entering the transfer orbit. So if you, at the moment, if you think of r and v are the values that we're using for the first orbit here. When we get to this point here, which is when it finishes the first orbit, we're going to initiate a change in velocity. That change in velocity is going to kick it out into this transfer orbit here. So that change in velocity we call delta v, which comes from the Greek symbol delta, which mathematically is used as change in. And we're going to use, for these equations, we're going to use it is, when I can type, it's 2,420 meters per second, or 2.42 kilometers per second. We also we're also given the time to change v, the time to this change in delta v, and we know from the information we're given, or I can tell you, that this is essentially after one orbit's complete, using these values. So when one orbit is completed. So these are some. You might want to comment on this code and just remind have a little notice what all these variables are. Now we're going to start actually plotting this graph. So put all our maths in here, all our working here. Okay, we're going to create a dynamic array called rplot. The initial value is the same as r. Rplot is basically going to be a list of all these positions that we're going to calculate using these initial conditions, and then once we've filled this, once we've calculated enough positions in this rplot variable, we're then just going to say, right, that value, plot that value as this orbit. So if you go back to this again, remember we're starting at a certain point. Looks like starting here actually, and those are the initial conditions given here, and then we're going to use them to work out all these positions all the way around here. Then when we get to the end of the loop, when we think we've got enough values, we then say that will be all in this rplot array, and we just say plot that array, and it's going to be an array of values. And if you look here, because it's going to be values of r, and r is a three-dimensional array, we don't need anything else to plot against, because we have the x and y, and we'll just plot the first column against the second column. So we know that this time to delta v here is how long it takes to complete one orbit. So while t is less than or equal to while t is less than or equal to that, we want to carry out the maths for the first orbit. Essentially, working out the position for every single orbit, so working out all these new position vectors given the initial conditions, the initial starting point of each orbit, the maths is actually exactly the same. The only thing that changes is the initial condition. So here we know the velocity. We know the initial velocity because it's the velocity at the beginning of that orbit. When we get to the end, we're adding velocity. So in the case for satellite, a rocket engine would fire, add some velocity to the initial orbiting velocity, and that means because of the orbital mechanics equation, that means if we've done that, then r must get bigger. It has to, for everything else to stay balanced. And what it does, it flings it out on this elliptical orbit, because the r used is the semi-major axes, which is like the average. So this r must get bigger. Now then, to then get into this bigger orbit here, we must have another change in velocity here, and we can work that out, because we know that the r of the radius of this big orbit is exactly the same as the radius of this sort of semicircle, this half orbit here, and so we know that the semi-major axis is going to be that, and we then, if we know that's the case, we need to know that, well, we know the velocity needs to be x big, however big it needs to be. We know what the current velocity is, so therefore we can work out the change in velocity, and we just say, well, we add that change in velocity to it. That will then get us in this big orbit here. So that's basically how it works. So we need to work out the magnitude of the radius vector first. So again, magnitude, if it was at an angle, if there were an x and a y value here, then that'd be, at the moment it's pretty hard to see because there's only one value. The magnitude is that, but that basically works out Pythagoras theorem. I think, yeah, and it's also out for you. And then we need to work out the acceleration, and you can do that using, again, and now we've worked out the acceleration, we need to work out what the next velocity is going to be. So we know what the initial velocity is going to be, and it's going to be plus the acceleration times change in time. And it's also going to be, and then it's going to be times the radius, and then all that, and it's going to be times radius divided by the radius magnitude. These equations, if you're kind of wondering where I'm getting all these equations from, I recommend they're all essentially one form or another of the main orbital mechanics equation. There might be another one in there, can't remember, it's a while since I wrote it. You just get yourself really familiar with them and what they actually mean, because the orbital mechanics equations are nothing like what we were used to seeing on Earth. The acceleration stuff is not. It's all based around, because there's no air resistance or anything, and a lot of the acceleration is self-generated by the gravity, because an orbit is just falling. You're just falling, but you happen to be travelling in one direction so fast that every time you fall, you miss the edge. So it's like if you think about just a cliff and lots of them in a row. If you fire a bullet off a cliff, a bullet's falling, and it falls at the same speed as if you drop a bullet from your hands. If you pull a trigger on a gun and drop a bullet at the same time, they'll hit the ground at the same time. But if you're firing your bullet off a cliff, it misses the edge of the cliff. The bullet hits the ground that you dropped. The other one keeps falling, but it's gone over a cliff, so it just keeps falling, keeps falling. And if you've got essentially infinite amount of cliffs and the bullet goes infinitely far, it will just eventually just keep falling, keep falling, keep falling, keep falling, just miss all these cliffs. And that's kind of what an orbit's like. T equals t plus dt. We need to update the time so that this loop doesn't go on forever, although you'll see that these loops, this actual program does take a long time to run. So now we need to update the rplot vector, so it needs to be equal to the original one, and we're just going to add on the end r next, which we calculated earlier. Oh, I forgot to add that line in. So after the v next, we need to now we know the new velocity. We need now to work out what the next radius is going to be. So it's literally just the original radius plus dt times v. So we just add that to the original radius. This list of radiuses that we're going to plot, because remember they're just position vectors, so though they're essentially coordinates themselves. It's going to say underline this because it's a dynamic array, and it's technically bad programming to not define an array's length originally and we're expanding it because the computer doesn't know how much RAM it's going to need to use, and you might run into problems if you've if you're writing a big program for lots of these in that had a small amount of RAM it could use. But in this case, we know there's no way of us knowing how long this array needs to be, and to make this code easily adaptable, and we know it's not going to fill the RAM quota, so don't worry about it. Now we just need to update all the values so that the next time this loop runs, it's all up to date. Okay, I was wondering why it's underlined. We want to hold the, because we're going to be plotting 3 orbits in a row. We want to put hold on so that they all stay on the graph every time we update it. And we're going to name this plot so that when we come to annotate the graph later, we can refer to this name in the annotation code. So we name it. We're basically creating a variable that is a plot. So we're going to use that array that I said earlier. So our plot, we want to plot the first column, and then we want to plot that against the second column, which is what that says there, and we're going to make it blue, sorry, and we're going to make the line shit. There we go. Is that going to update? Hang on, why is it giving us a little error here? I know why. There we go. Right, brilliant. Right, that's the first orbit code done. Now we want to plot the second orbit. It's good just to break up your code so if someone's reading this, they know which bit does which. As I said earlier, the actual loop is going to be very similar, but there's some things that we want to do before. So before we were plotting a whole orbit, and to plot the whole orbit, all you need to know is you need to know the amount of time it takes to do that orbit, and then which you can work out using the orbital mechanics equations, but we were given that in that case. So we know the time it's going to take to do that orbit, but this one is different. We don't want to do the whole orbit, we want to do half an orbit. And you can use, it's perfectly okay to use, basically work out how much time it's going to take to do the whole orbit, just divide that by 2, because that's how long it's going to take to do half the orbit. However, another way of doing it, which I used, and I think is just good to know because it's just teaching you a bit more about orbital mechanics, is you can work out, there's equations that tell you the angle between this sort of starting radius here and whichever point it's on. And when it gets to 180, when it gets over here, you know it's completed half the orbit, and you can just say when that angle is 180, stop doing this. So we're going to need to introduce, first of all, we just need to reset the rplot array. So it's just going to equal the r, which at this point is the radius at the end of that. Now we need to have some other things, so we're going to need the angle theta, where it equals 0 to start off with, we know that. We're going to need the periapsis, so the periapsis is the lowest point, the apiapsis is the highest point. The radius of the periapsis is going to be the beginning one, and the angle theta is basically the angle that you're at compared to the periapsis. So RP is going to be the periapsis, and that is equal to R2 because it's the start. We know the start point is the lowest point because we've added, we're about to add this delta V, we're about to add some velocity to it. Now we just need to calculate the magnitude of that. Okay. Let's find out where we're going. we need to work out the initial. Oh, now we need to add some velocity to it. So equals v plus delta v, which is the variable we declared earlier, times and then we need to update v next, and then we can set about doing these equations. So in this, as you can see here, what I've done is I've added delta v to the velocity vector, but I've only added it on in one direction. If I had just added it, it would add it to all three. So it would add it, if we go up here, it would add it to the x, y, z. We only want to add it to the y vector. And if I'll just bring you back to this again, because if essentially we're back here at the starting point. So I said earlier we're at 6 o'clock, and that was wrong. We were starting at 3 o'clock, and that means we're, you know, as I said, the velocity is at a direct perpendicular angle from the radius, and if we add velocity to all three, it's going to scoot off and send it flying off somewhere else, and also down. But we only want to put it in one. We only want to add the velocity perpendicular to the orbit, to the radius. And because we know at the beginning, we know at 3 o'clock, we know that perpendicular is in the y direction, and therefore we can just add it in that way. In real life, you can't just add 2.4 kilometers of velocity in a second, unless you've got some ridiculously. In fact, I don't think that's possible even for like an F1 engine or something. From the Saturn V, it's just not possible. So you have that burn spread out over a period of time. So you'd start the burn, say here, and you'd finish it when you got here, and that kind of averages out, or basically means it applies, on that perpendicular thing. You don't want to just, if you just burn here, because you're not going to add that much velocity, it's a really inefficient way of adding the velocity in that second, because you start going down here and perpendicular, also adding them velocity, just like in other directions. You don't necessarily want it. If you want to understand more about how you'd go about altering orbits and things like that, I'd recommend Kerbal Space Program. It's basically based on a miniature version of the solar system, so the maths and stuff is all the same. You just deal with smaller values, and you'll inevitably crash a lot. It's good fun. So that's why we're adding the velocity in just the one direction here. Right, now we can go about where am I? Now we can go about working out the position vectors for all the second orbit. So while theta is less than pi, because pi is half it, so not equal to. Now the reason I haven't just said pi, because when you work out theta, and because we're using 1 second gaps, you'll basically get all the way, you'll be working out all the position, you get right to the end, just to the end, and then you'll be here, and that means that the angle is now, instead of being between there and there, is between the radius is coming off this way and then going across there, so it's under here, not over, and that will be less than pi as well. So you basically will just have it, you end up in this infinite loop where it just never quite actually reaches pi. So this is the closest I've got to it being pi and it working without it, getting in some infinite loop, which yeah, so that's why I recommend that. So now it's very similar to the before in terms of actually going about. The only difference is we're going to end up calculating theta. So I'll just whiz through some of this stuff. t, again we're going to update t. And then we want to update the plotting array. It's going to give us the underline again, update all the velocities. Now I want to calculate theta. So we need the dot product. So you want dot, it's pretty easy in MATLAB that you don't actually have to do it yourself. You just give it the values and it will do it for you. We'll give it the vectors and it will do it for you. If you don't understand why we can dot product, we're going to work out the angle between two vectors, remember, not between, because although the two, so the radiuses are essentially position coordinates, they're also vectors. So we're working out, so you need the dot product for that. So we want then the cosine of theta. If you don't understand why we're using these equations here, like the dot product and then stuff like that, you should go and just Google how to work out the angle between vectors. Pretty simple stuff. And then we invert that cos to get theta. Right. Now, one of the things is we want to have one of the things we want outputted is when the satellite reaches the third orbit, and basically when it gets to the end of this, it will be here, so it's reached the third orbit. So we want to just output the time at that point. And you'll see from when I run this code in a bit what takes the real amount of time, because this is a big giveaway. This output here is a big giveaway as to where we are in the code. You know, we've essentially done 2/3 of the code, two of the loops, two of the main parts, but actually that appears almost instantly, and it doesn't actually output the final value, the final graph, till quite some time afterwards. And so it shows that how quickly it can do this bit, but how long it takes, how many individual positions there are on this, because if we're calculating in terms of seconds, and it reaches this at the end of 24,000 seconds. Or just over 24,000 seconds, which I don't know how long that is in days, but I think it's a bit. And then if consider how big this orbit is compared to that. It's got to work out every second value, the value every second there, and it will go up. I think it goes up, like hundreds of thousands or something. It's how many values it works out in that time, but I can't remember off the top of my head. So display. And now we want to plot the orbit, and again we're going to name it. So orbit 2 the plot, and that is because later on we're going to annotate this graph, and we need the names of the plots to do that because there's different ones. Right, that's the third one done. The second one done. Now let's do the third one quickly. Now the third one is really pretty simple. It's basically exactly the same as the first one because we're not working out any theta or anything, so we can just copy and paste that code. But if I just check the actual loop is the same, but there's a couple of things we need to do before that because we don't know some things. So the first thing we need to do is work out or reset the plotting array, and we're gonna add t start, which is the time the start of the orbit. Now the reason we're going to do this is because we're doing a loop here, to work out all these positions, and we're going to do it based on time. The problem we have is we don't actually know how long this orbit is going to take, so we have to work that out, and then we have to then add it, because t is a running count. We have to add that to the initial value of t. So we need to store this starting value of t here, work out how long it's going to take, add that to t start, and then that total time will give us how long it's actually going to take to do this orbit, and then we can use that in the condition for our loop. So that's that. Then we need to work out the orbit period, as I said, so how long that orbit's going to take, and these use the orbital mechanics equations. Times part. Is that done? Oh, have I done this? Just give me an underline. Let me just check the notes here. That's right. Work out the orbital velocity. That should be divide, and then the delta v. So the reason we need delta v, so the orbital, so let me just explain what's happening here. The orbital period is how long it's going to take to do an orbit of this radius here. We don't have, but that requires a higher velocity than the velocity we have here. So we need to work out that velocity that's going to require to do this orbit. Then we're going to need to work out the delta v required, because I said it's going slower at this point originally than it needs to do this orbit. So we work out the difference in that velocity. We then add that velocity to this to get the required velocity to do this orbit, and then we can work out the rest. Remember how I said so the velocity is a vector, so at this point it could be over, it could be over two axes, so we just want the magnitude of it. We want to add that delta v, similar to how we did it before. Now the difference between before and now is I'm using -1 instead of 1 on the y-axis, and that's because we know we're going we know we're going up here, and we get to this point here at 9 o'clock, and we know that the satellite's on its way down. If we add the velocity on the y-axis positive, that's going that way. Adding velocity this way, it's going to slow it down even more. So it'll actually reduce this orbit here. It might end up crashing back into Earth. We want to add it in the way it's going, so it has to be -1 because it's heading down. And v equals v next. Sweet. Now we can start the loop, and the condition is while t is less than t start plus orbit period. Remember I said, the starting point is t start, and the orbit period is how long it takes. So the end of this loop will be, you know, when it finishes that, the total time when it finishes. Let me just check the contents of this loop, because I'm pretty certain it's identical to the initial one. So we work out the R length, we work out the acceleration, work out V next, work out R next, we update the time, work out, yeah. So you can just copy and paste all this, because remember, it's just going in a circle again. It's not doing any fancy with angles. So and there you have it. That's exactly the same. Now we want to plot this orbit 3, this third orbit. So again, we want to name it. First column against the second column. We want it to be in black. To be 1. There you have it. Okay, now we want to annotate the graph. Okay, so this legend is saying you want to we're going to label these orbits or these plots, which are plot orbit, you know, orbit 1, orbit 2, orbit 3, and we're going to label them with the labels orbit 1 for the first orbit, 2 for the second, pretty self-explanatory stuff. So if you'd named these plots something else, if you'd named it like 1, 2 and 3, you'd have to change this to 1, 2 and 3. This bit here, this bit is the actual like titling, as it were. I want to give it a title. Label the x-axis. The actual x and y axes have the same thing. They are both the altitude in meters, but they're in, you know, different axes. There we are. So that is, we'll close this down. That is how you work out, you know, write a program to works out the orbits. And I'll just run this. I have to save it. Oh, I've got a error in line 30, which is typo. Oh, I've got an error in lots of them. In line 57, that needs to be V next. Will it run this time? Nope. We've got an error in line 90. It's the same line every time. 91. Need to learn to type. Run that. There we go. That's correct. See how quickly it fired out when it reached there, and then this is how long it takes to work out that third orbit. We'll just wait for that to come through. If you have a faster computer than mine, it will work this out faster. But if you remember it's not to work out every position vector, it has to run all these lines of code every time. So that takes some time when you've got a lot of them to do. I think it takes. Here we go. There's a line in my labeling code's wrong, but the rest of it's correct, and you can see from here, like, that is the correct output. You know, the labels aren't there on the end, but on the axes, but the output's the same. And that is how you work out the transfer orbits given as a set of initial values. The things to consider in this are, and there are ways of working out mathematically, but they just add a lot of complexity and a lot of lines. But if you weren't given the initial values that we're given, where the time delta v is exactly one orbit, you would need to then work. I've closed down the thing, so I can't get it back up again. But you'd need to work out what angle you're at, to relative, what angle the velocity needs to be added so it's at perpendicular to the radius. In this case, we're given really nice, easy initial values, so we can just make it exactly up the y-axis, exactly down the y-axis. That's something to bear in mind if you do this with a more complicated example. Thanks for watching.